Hello, everyone. I'm Louis Esperet from Grenoble, and I'm going to talk about sketching distances in graph classes. And this is joint work with Nathan Harms from Waterloo and Andrei Kopowski from Grenoble and Moscow. So I'm going to start talking about adjacency labeling first. So you consider a graph class F, and you denote by Fn the subset of graphs on n vertices in the class. And your goal is to assign labels to the vertices of all the graphs in the class. Labels are just binary words in such a way that if you give the label of U and the label of V in some graph G to a decoder, the decoder will know whether U and V are adjacent only by looking at the two labels and without knowing the graph G. So the decoder only depends on the class. It doesn't depend on a specific graph G. The input are the two labels of U and V, and the decoder says U and V are adjacent, or U and V are not adjacent. And your goal is to minimize the size of the labels, the number of bits of the binary words. All right. And let's start maybe with an example. Interval graphs. Interval graphs they are the intersection graphs of intervals of the real line. So each vertex corresponds to an interval, and two vertices are adjacent if the corresponding intervals intersect. And I claim that there's a simple, you can put adjacency labels of size 2 log n plus 2. And the reason is that if you have an interval graph on n vertices, you can always make sure that the ends of the intervals are integers between 0 and 2n by moving the ends a little bit. And then the label of each vertex is simply the coordinates of the two ends. So each takes log of 2n. So it's 2 log of 2n, 2 log n plus 2. Because the decoder, given the ends, the decoder, it's very easy for the decoder to decide whether the two intervals intersect or not. All right. And it turns out that this log n range is the first interesting range for adjacency labels. Because in most graph classes, vertices, they're not really, you have very few twins, very few vertices with the same neighborhoods. So most vertices would have to have different labels. So you would need all the log n bits in any reasonable graph class. So log n is the first interesting range. And the natural question is, which graph classes have adjacency labels of order log n? And here I added the condition that the graph class is hereditary, which means that it's closed under taking induced subgraph. And there are many natural reasons why you would like to consider hereditary graph classes. They're more regular, but also if you have adjacency labels for a graph G, you also have adjacency labels for any induced subgraph. So it's a natural property that's closed under taking induced subgraph. So all classes that we are going to consider almost are hereditary in the remaining of the talk. All right. So you would like to understand this question, which hereditary graph classes have adjacency labels of log n, but for this you need to understand how to design adjacency labels, but you also need to understand how you can prove lower bound on adjacency labels. And there's one basic lower bound, which is the counting lower bound. Assume you have adjacency labels of size k in your graph on n vertices. So if you're given the labels of all the vertices, so this is k times n bits, then you can recover the graph. Because for any two labels, you know whether there is an edge or not, if you have the decoder. So kn bits allow you to recover the graph G. But you only have 2 to the kn possible words on kn bits. So in your class, you must have at most 2 to the kn graphs of order n. So if you put it the other way around, it means that any class F, for any class F, you need adjacency labels of at least 1 over n times log of Fn. Okay, n is always the number of vertices in the graphs that you consider. All right, so this is the counting lower bound. You can't beat this lower bound. And so maybe let's see an example. The class of all graphs, you have 2 to the n choose 2 graphs. And 1 over n times log of this is exactly n minus 1 over 2. So you need at least n minus 1 over 2 bits for labels for the class of all graphs, and n over 4 for the class of all bipartite graphs. And it turns out that these two bounds are sharp. You can prove this. There are adjacency labels of this size. Right, but the natural question is, when is this counting lower bound almost sharp? And there's a conjecture, there used to be a conjecture called the implicit graph conjecture of Canaan, Naur, and Rulich. And the conjecture was saying that basically if this counting lower bound is of order log n, then you do have adjacency labels of size order log n. So it's the first range that we consider the interesting range of log n bit adjacency label. The conjecture was saying that if this counting lower bound has the same order log n, then you can also find adjacency labels of size log n. And this was disproved very recently by Hatami and Hatami. And the counter example is non-explicit. It's just an existential proof. But it's a breakthrough, really. All right, this was about adjacency label. Let me now talk about adjacency sketching, which is the randomized version of this. So in adjacency sketching, instead of putting deterministic labels on the vertices of the graphs in the class, we're going to put randomized labels called sketches. And now the decoder doesn't have to guess correctly whether U and V are adjacent with probability 1. We only ask it to guess correctly with probability at least 2/3. Okay, for any U and V, the probability that the decoder is wrong is at most 1/3. All right. And now you can ask the same question: which hereditary graph classes have adjacency sketches of size constant? Because now constant is the natural first interesting range. It's not log n anymore, it's really constant. Already looking at constant is interesting. Which graph classes have such adjacency sketches of size constant? Well, let's see maybe one example. Look at planar graphs. Planar graphs, they have an orientation in which each vertex has out degree at most 3. It's just degeneracy that gives you this. So what you can do is the following. You can assign a random color to all the vertices of the graph, a random color with constant number of colors. I wrote 18 here, but take any large constant. And now the sketch of each vertex is going to be its color followed by the color of its out neighbors, right? So it takes constant size. You only have 4 colors to remember. And now what the decoder does, given the sketches of U and V, it checks whether the color of U appears in the colors of the out neighbors of V, or the color of V appears in the colors of the out neighbors of U. There must be an edge between U and V. If they are adjacent, there is an edge, and it has to be directed in one way or the other. So the decoder will always guess correctly if they are adjacent. The decoder will say they are adjacent. But if they're not adjacent, the random colors, because of randomness, you have a very good probability that the color of U will not appear in the colors of the out neighbors of V, and vice versa. So there's a good probability that the decoder will say, no, these two are not adjacent. All right? So this is a fairly simple sketch for planar graphs. All right. So we saw lower bounds and for adjacency labeling. What are natural lower bounds for adjacency sketching? And there's a very nice observation of Harms, which is that once you have adjacency sketches, you can de-randomize them, and the cost is only logarithmic in n. So you only pay a log n multiplicative factor when de-randomizing. You can transform adjacency sketches into adjacency labels in this way. So the lower bound that we had for adjacency labels, it still holds for adjacency sketches, but there's a small logarithmic loss. So any class needs adjacency sketches that have at least 1 over n log n times log of the number of graphs in Fn. All right, so this is still a counting lower bound. But previously, we only had this kind of counting lower bounds for adjacency labeling. Now we have a new, very interesting bound, which is completely different. And And this comes from communication complexity. So this was proved by Harms, Wild, and Zamariev by making a connection between randomized communication complexity and adjacency sketches. So they proved that there's another obstacle for having constant size adjacency sketches. It's the presence of large half graphs in your class. So what's a half graph? So you take a graph in your class, and this would be two subsets of vertices, disjoint subsets of vertices, numbered 1 up to k and 1 up to k. And you have an edge between I and j if and only if I is at least j. Okay, so this is a half graph. And if you do have such half graphs of arbitrary large size in your family, inside the graph of your family, then you can't have adjacency sketches of constant size. And the reason is that because if you did have this, you could encode the greater than problem in communication complexity, and that doesn't have any randomized, constant randomized communication protocols. All right, so these two very different low bounds now, instead of just one. But it was conjectured in the same vein as the implicit graph conjecture, that if these two obstacles, you don't have these two obstacles, then you do have constant size adjacency sketches. So this was conjectured by Harms, Wild, and Zamariev. So if you don't have too many graphs in your class and you don't have large half graphs, then you have constant size adjacency sketches. But this was also disproved by last year by Humbert, Zumian, Hatani, and Hatani, also with a non-explicit counterexample. All right, so this is wrong, but we still have the very natural question: what are the graph classes that have constant size adjacency sketches? But maybe hereditary is too general. Maybe you need to understand, make the class more regular to be able to say something meaningful. And one way to make hereditary stronger is to ask for being monotone instead. So hereditary means closed undertaking induced subgraph. Monotone means closed undertaking subgraphs. So if you're monotone, you're hereditary. But monotone is stronger, but it still encompasses many interesting graph classes: planar graphs, any minor closed class, k-colorable graph. So if you can say something about monotone classes, it's still interesting. So what can we say about monotone classes that have constant size adjacency sketches? We've seen one, planar graphs, but are there others? So what we proved, first result is that for monotone classes, having constant size adjacency sketches is equivalent to having bounded average degree. So planar graph, they have bounded average degree, so it's good. And the proof that I showed actually works for any class of bounded average degree. But the hard part is to prove the converse. If you don't have bounded average degree in your monotone, then you don't have bounded size, constant size adjacency sketches. And for this, we use tools from communication complexity, discrepancy. So this is our first result. Now I'm going to talk about extension of this adjacency sketching to distance sketching. So there are many ways to define distance sketches, but since we are interested in the constant size range, we have to be very humble about what we ask about distances. But asking the precise distance, it's impossible. So let me explain two interesting variants of distance sketching. The first is called small distance sketching. So you're given an integer r, r is fixed, and now the decoder has to make the distinction between the distance of u and v is at most r, or the distance between u and v is more than r. And again, you have to guess correctly with probably at least 2/3. And we want sketches that are independent of the size of the graph, but they can depend on r. Right? The size is at most some function of r. So this is small distance sketching, and if you have such sketches for all r, with a size that depend on r, then you're said to be SD sketchable, small distance sketchable. So this generalizes having constant size adjacency sketches, because if you take r equals 1, being a distance at most 1 or more than one is just being adjacent or not. So if you're SD sketchable, you have constant size adjacency sketches. So this was the first variant. Another very interesting variant that has been studied, I'll come back to that, is ADT sketching. So approximate distance threshold sketching. So here you have some constant alpha, some real number, at least one. And now you want to make the distinction between the distance is at most R or the distance is more than alpha R. So alpha says 1,000, at most R or more than 1,000 R. And now the difference with the previous item is that now we made our life much easier, but we want to gain, and the gain here is that I want sketches of size independent of n, the size of the graph, but also independent of R. Okay, sketches are really some constant, independent of R. R will grow, maybe it can grow something that depends on n, but I want sketches of constant size in this case. So this is quite different from the other one. And again, if you have this for all R, you're set to be alpha ADT sketchable or just ADT sketchable. Okay, it has to be the same alpha. All right, so we have these two notions. The second one has been quite well studied in metric theory. You can ask all these questions in any metric space. You don't need to be in a graph. And there are not many general results in metric spaces, but one very nice characterized of normed spaces that are ADT sketchable. But normed spaces are very specific, very different from metric spaces coming from graphs. Right. Okay, so what can you say about small distance sketching, approximate distance sketches? Which classes have such sketches of constant size? Let me just show you one example of a class that has such sketches first. So let's take all hypercubes. The fact that this class is small distance sketchable is just a consequence of a very classic protocol, but for computing the Hamming distance, two-way communication protocol for the Hamming distance. And in particular, it implies that also sketching the adjacency in hypergraph. You can do that with constant size sketches. And in particular, you can do that for all induced subgraphs of hypercubes. Okay, because it's closed undertaking induced subgraph, having adjacency sketches. So you can really, if you take the class of all induced subgraph of hypercubes, you have adjacency sketches of constant size. So it's quite nice. Well, the class is also ADT sketchable. It's a result from 2000. But it's a nice class. One quite fairly interesting thing is that, so we've seen that induced subgraphs of hypercubes, they have adjacency sketches of constant size. But the first result that I showed you implies that subgraphs of hypercubes do not have adjacency sketches of constant size. Because this class of subgraphs of hypercubes, it doesn't have average degree, bounded average degree, but it's monotone. So the consequence of our result, it doesn't have constant size adjacency sketches. And this is the first explicit counterexample to the conjecture of Harms, Wild, and Zamaridis that we have seen. All right, so let me go back to small distance sketching. Again, we want to make the distinction between distance is at most R, distance is more than R. And to characterize the monotone graph classes that have such sketches, I'm going to have to define the notion of bounded expansion. So here, the term expansion doesn't refer to expander graphs or expansion in expanders. It's really expansion in sparsity theory. It's the same name, but it's not the same notion. So you said that the class has bounded expansion if, for any R, when you contract connected subgraphs, disjoint connected subgraphs of radius at most R in any graph in the class, the average degree remains bounded by a function of R. So you contract things of radius at most R, and the resulting graph, the minor that you get, still has bounded average degree, bounded by a function of R. If you have this for any R, with a specific function f of R, then you have bounded expansion. But this contains many interesting graph classes, minor closed classes, sparse random graphs, bounded degree graphs, graphs with bounded Q or stack number, many classes that have some geometric definition. All these are bounded expansion. And such classes have very nice algorithmic properties. You can do first order model checking in linear time, many other important properties. And what we prove is that a monotone class is small distance sketchable if and only if it has bounded expansion. And the proof is very similar to what we did for adjacent sketches, except that we need a fairly recent result in extremal graph theory. All right, so this was about small distance sketching. Let me go to approximate distance sketching. Again, we want to make the distinction between the distance is at most r and the distance is more than alpha r. But now the very important constraint is that the length, the size of the labels doesn't depend on n, doesn't depend on r either. It's really a small constant, say 2 bits, for instance. So we prove that any minor closed class has such sketches. It's a really very easy consequence of classical results in metric theory. And so minor closed classes, if you think in terms of expansion, as I define it, if you contract anything in a graph in a minor closed class, you remain in the class. And your average degree doesn't really increase. It's still bounded by a constant. So minor closed classes, they are the classes of constant expansion in this sense. And then you can ask, what are the classes of polynomial expansion? They are very interesting. They have sublinear separators, or exponential expansion, or you can ask many questions and look, it's a hierarchy of classes. So maybe all classes of bounded expansion are also ADT sketchable, or maybe not. But so we prove negative results. We prove that there are classes of arbitrary, slowly growing expansion that are not ADT sketchable. They even have maximum degree 3. So constant expansion, they are ADT sketchable. And if you take just a slowly growing expansion, then it doesn't need to be ADT sketchable anymore. But we still prove that if you're monotone and ADT sketchable, then you have bounded expansion. And in particular, using our first result, you are SD sketchable. For monotone classes, this ADT sketchable implies SD sketchable, and it's interesting. And our proof is fairly complicated. It takes a lot of different pieces, but we don't have any direct simple proof of this result. All right, so let me conclude now. I haven't talked much about proofs, so they combine structural graph theory results, extremal graph theory, communication complexity. We still haven't really answered the original question, which hereditary graph classes have constant size adjacency sketches? It's the same problem as asking which problem have constant randomized communication complexity. It's a very difficult question, but there are very nice conjectures about this. We still don't know exactly, we haven't characterized exactly which monotone graph classes are ATT sketchable. The minor closed classes have this property. They have bounded expansion, but we don't know exactly what the right answer is, what kind of natural obstruction we should have for this. And one thing we haven't done either is optimize the factor alpha in the definition of approximate distance threshold sketching. Though maybe in a certain number of cases, we could really take alpha to be very close to 1. For instance, it might be the case that planar graphs, they are 1 plus epsilon ATT sketchable for any epsilon. This would mean that for any epsilon, you can really make the distinction between 2 vertices at distance at most r and 2 vertices of distance at more than 1 plus epsilon r, with sketches whose size would only depend on epsilon, not r. That's possible, but the current tools that we have, they are way too, we can't prove this at the moment. Quite far from that. All right. Thank you very much for your attention.